Hello and welcome to this tutorial session. In this tutorial session, uh, I will be recapping the whole last week's lectures. Okay, and this tutorial session is regarding the smart grid basics to advanced technologies. This is taken by me, Mohammed Owais, the Prime Minister Research Fellow, Department of Electrical Engineering. So what we are going to read here over this is that first we will do a recap of the things which we have learned in over a week. Then we will do some questions to increase our understanding of the topic. So basically, we will start here first the energy management. Energy management in a DC microgrid. I have already talked to you about various type of microgrid, DC microgrid and AC microgrid, and what are their advantages or like that. So basically, a DC microgrid works connect in a grid connected mode. A simple, a diagram of L filtered grid tied DC microgrid is being shown here on the right side. This is connected to the nopal RT. There are DC loads over here. Then there is the DC microgrid, which is connected through this AC load. This is the point of common coupling. Point of common coupling. This is connected to a grid. There are AC loads over here, and also this is a control logic diagram. So basically, the offset output of the current and voltage sensors are given in analog to just a second. Okay. Now voice is coming? Okay. So on the right hand side, this is a block diagram of L filtered grid tied DC microgrid. In this, the offset output of the current and voltage sensors are given ADC pins of DSP launchpad TM this is. So basically inside the DSP controller, the ADC pins read three-phase voltages and current with the DC link voltage. Now, by using the class transformation, these three-phase voltages can be converted to the stationary reference form. And the control logic this is the control logic which generates the modulated voltages for generating PWM pulses, and it is through EPWM pin of a DSP. So basically, in a grid connected mode, the control logic is given here. This is the reference voltage. This is the DC. So it always compared with the reference voltage. Then it goes toward the PI controller. Then after that, the PI controller regulates this DC voltage. PI controller regulates the DC voltage at a reference value and generate AC reference power. And from that AC reference power, active current difference is generated at the inner controller, which requires the current reference. Then after this, the obtained AC current difference is compared, which is this AC current difference. It is compared with a measured current, which will give an error. The error is processed through proportional and resistant controllers for generating the required modulation voltages. So basically, modulation voltages are generated after this step. Then these modulation voltages are used for single SPWM generation through EPWM pins of our DSP for switching converter switches for IGBTs. Okay, so here PI is, the control function of the PI is given as Kp plus Ki by S for PR, which is proportional plus resonant. Its control function is given as Kpr plus Kir divided by S square plus omega square. So this is how a laboratory prototype of a grid-tied DC microgrid is shown here, where on the left side this is a DC microgrid where PV is connected, BSS is connected, Opal RT is connected. Okay, this is connected to a DC bus, and after that it is connected through the V out and V in. Now this is a DSP logic where the pulses are given through this microcontroller. Okay, then here it is a grid part which is connected through point of common coupling. Okay, this is a laboratory prototype, or we can say a laboratory setup. Okay, so basically this is like this. This control logic is implemented in a floating point Texas DSP digital signal processor, and in this the grid is, whenever we develop a simulations in a laboratory, then we have to simulate everything. So the grid is emulated through Synergia grid emulator. So and the rheostat and bulbs load are used as a DC and an AC load. And the behavior of DC microgrid is emulated through a power amplifier. Okay. Now, Semicaron three-phase IGBT-based PWM inverter is used as a bidirectional DC to DC AC converter between the DC bus and the microgrid. Okay, so next we have here is a hardware demonstration. So in this module, we are very much interested in showing how the hardware demonstration of an energy management. I've already talked about in the previous lecture why is energy management is very much essential, and what are their benefits, how is it implemented. Okay, so in a hardware demonstration test cases, first test case is taken in where the DC microgrid is emulated through a power amplifier, and the control system of the interfacing converter, which is AC grid and a DC grid, is implemented through a DSP controller. So basically, what we have, there is an AC grid and a DC microgrid. It is connected to the DC. This is connected to AC bus. So between this here, it is implemented through a DSP microgrid. What has been done in the test bed that interfacing converter has given the responsibility of controlling the DC bus voltage, which is at 400 volts. In the first case, we observe that if the sum of the power generated by PV and BSS is more than the DC bus load, the power flow from the DC bus, then what will happen here is that then the power will flow from the DC bus to the AC grid. So in order to demonstrate this type case, we assume that power generated by the PV, which is the solar, and the battery energy storage are constant, and the DC load is varied in steps. Like it is after a certain time it is increased, then after a certain time it will also increase. So when we look at DSO, we can clearly witness the decrease in DC load increases the current magnitude, and if we look at the power amplified circuit, which is positive, means that the power is flowing from the DC to AC grid. Likewise, in the second test scale, the power generated by PV and BSS is less than the DC load, which is connected to the DC bus. So from here we can see that if we observe the increase in DC load reflects the current magnitude, but as we know, the power generated by PV and BSS is less than the DC load, the power amplifier sign will be negative, which means the power will flow from AC grid to the DC grid. And the voltage at the DC bus is always regulated at the 400 volt. So from these test cases, we have analyzed that how the energy is exchanged between an AC grid and the DC grid. It is all based upon the power generated by the BSS. Okay, like if the power generated by BESS and PV is high, or we can say higher than the DC load. So what will happen here? The extra power will go, or we can say flow, from DC to AC, DC bus to AC grid. But if how we can see here, because the power amplifier which is connected between an AC to DC, it will give positive. It shows that power is flowing from here. But if power generated by BSS and PV is lesser than the DC load, then what will happen here? Power amplifier will give negative sign and power flow from AC grid to DC load bus. So this is how energy is managed in a DC AC microgrid. So what we conclude here from there is how to use the DSP controller in application of a grid integration of a renewable energy sources in a DC microgrid. And the main benefit of this lecture is that you can learn how to control the system based upon the DC microgrid. Okay. So basically, now in the next we are going to see power hardware in loop. So in the last lecture, I have talked to you about regarding the various hardware in loop. There are two types: power hardware in loop and simulation hardware in SHIL. So basically, this is a simulation platform which which will implement various techniques. For example, here this is RSCAD, then it is scaled down to a card which is known as GTO card. Then it is given to the power amplifier. Then from power amplifier it is given to the volt DFIG test bed, which is a doubly fed induction generator. Then from here it is given to the voltage and current sensor, and from there it is given to the filter. So basically this is a demonstration of a simulation platform in a hardware which is using power hardware in loop. So this is a setup of doubly fed induction generator where this is an FPGA controller. Here it is a DSO. Then this is connected choppers, various chopper circuit. Then these are GSC and RSC. And this is the induction machine, which is, and there is a DC motor. And these are all GTAO cards. Okay. So basically, demonstration of the card is here. You can, here it is the function generator which is generates various functions. Then it is given to the card. From here this card gives to the filters and the real-time simulation has been done. So basically Input of the voltage and current sensor sensing signals from the power hardware devices comes from there. Okay. Now, as I have said here, wind energy uses DFIG hardware setup. What it is, doubly fed induction generator it is used, and that's why the wind energy always generate electricity in a AC form. So basically, in the first there is a wind emulator. So there is a three-phase rectifier which is giving the supply of 415 volt 50 hertz. Then the variable armature is given voltage which is 220 volt 10 ampere. Then this is a chopper. What it does, it emulates the wind characteristics, what is like a real wind turbine works. Then it is given to the DFIG and back to back VSC. And after that, it is given to RTDS, which does a real time dynamic simulator and a power amplifier over there. Okay, so this is how DFIG hardware setup look like. Okay, so now I will go in detail. Just a second. Okay, now this is a distribution system which has been shown here in the figure, which has been shown in the figure. It is of IIT Roorkee distribution system. Here it is a utility. It is connected through a step-down transformer which is known as T1 33 to 11 kilowatt. Then after that, there is, we can see, a bus no, number 1 and another bus 2. It is connected through a switch which is like here. Okay, so basically there are various battery locations over here. These are PV locations. These all are solar PV locations. Okay, and these are the diesel generator. So this is a schematic of IIT Roorkee distribution system. Okay, so ancillary support. So ancillary support from the virtual synchronous generator in an islanded mode. What it does here, there is a diesel generator which has a total capacity of 6 MVA and a considered capacity of 4 MVA. Then the solar panel which are shown here, all these blue points are the solar panels. They are operating under the MPPT mode which have a capacity of the 2.8 megawatt at 35 different locations. Okay. Th- Then comes the battery energy storage system. So basically, BSS is a battery energy storage system which operate in a grid connected mode. There are various modes of operation. First, the increased penetration of PV, voltage regulation, peak load shaving, uninterrupted supply, power supply, and there is also okay. It has a total capacity of 800 and it is located in a distributed manners at 5 different locations. Okay, so BSS are given at the 5 different locations: A, B, C, D, E. So BSS locations are A, B, C, D, E, and then comes the virtual synchronous generator which operates in a grid connected mode, have a capacity of 2.5 megawatt. Okay, Then there are various types of load: departmental, residential, apartment, hostels, and this has a total load of 7.8 MVA. So this is basically an architecture of islanded mode of operation because there is no grid connection. Okay, so the power hardware in loop implementation schematic diagram is here. First is the RTDS, which is the real dynamic simulators. In this, the voltage measurement, current source are there, which are connected to through a DAC or ADC. Then comes the power interface, where the amplifier circuit is there. DAC is there, which is used to scale the signal, and then the current. DAC is generally known as digital to analog conversion. ADC is analog to digital conversion. Okay, so this is how. And after this, the power processor and energy storage are there. So basically, PHL implementation of a schematic with a VSG control is shown here. First is the simulated power system of the IT Roorkee distribution network. Then after this, there are various switches are there and power amplifiers, and it is given to the monitoring station also. So it will help in the monitoring of all those things. This is the PHIL setup. This is IT distribution and network inside RTDS. This is a controlling desk which will control everything regarding the energy management. Then, then what will happen here? This is the IT Roorkee network monitoring window which will monitors all these things. Then comes the power amplifier, and these are the what do you call it? It is the MCBs. Okay. So in the first result, the case study disconnection of the solar panel. So what will happen here in the case study? It shows a drop in the system frequency. Okay, after the disconnection of solar panel. Second one shows the scaled up of VSG output. Okay, in the first case. In the second, it also shows the runtime actually drop in frequency. Like this is going over here, then the frequency is dropped after the disconnection, then it is again restored by the VSG power output. Second is the connection of the induction motor load. Whenever the motor load is connected, how the frequency varies and how the load is varied. Okay, power output is varying. Now come another here in this, which is the scale study of the disconnection of a induction motor load. So basically, here in this, what has been done, first it shows the drop in system frequency. Okay, it shows the scaled up VSG output. Okay, so what are the various challenges faced in the modeling of the IT Roorkee distribution network or any simulation model? So what happened here is that in order to perform the frequency stability study and observe electromagnetic time scaling strength, modeling accuracy need to be maintained properly to preserve the original characteristic of the network. Cables model using pi model, and only nearby loads are combined to form 72 into 6 nodes of RTDS. In a diesel generator, 6 models are used to represent the generator, which includes excitation systems, power system stabilizer, and the turbine governor models, which allow them to run in a free mode. Okay. Uh, Capacitor bank used for the proper support is also used for the proper voltage support. Then comes this. solar photovoltaic. So basically, in order to model the photovoltaic, the average modeling of the converter is not appropriate for the transient study. Modeling of the converter need to be done in a small time step section. After the PI control thing, even for a two equal inverter, the PI parameters are not same because the RTDS interconnection between rack 1 and rack 2 was made with a YY interface transformer. PV module associated are also different, which results in a different step response for each phase inverters. Okay, so these are various challenges which has been faced regarding the modeling of the IP Roorkee distribution system or modeling of the cable or the diesel generators. Now, other challenges which have been faced are the control formulation. Okay, let me give you just a second. Okay, so what we are learning from here is that the various challenges. So another challenge is the control formulation at the FPGA level. Okay, so uh, various challenges are faced for the control formulation, like the proper switching frequency determination for DC to DC converter and DC to AC converter. It is one of the challenge. Another is the proper bandwidth determination with inner and outer control loop to avoid interference between different control loops. Another here is the proper designing of counters in a discrete model of control and the inclusion of appropriate number of delay blocks. These are the challenges faced at the FPGA level for the control formulation. Another here another here is that the filter designing of for interfacing in inverter, because in the inverters which are interface, there are filters are designed like you can see here in this, just over here, the filters are designed. Okay, so basically what happens here is that the filter designing is also a very important challenge. Like it can create a resonance condition if we improperly design the filter. It can create a resonance condition for LC-LCL filter. It also determines the active passive damping is required or not. Whether also helps in maintaining the quality of power being injected into RTDS. Otherwise, can lead. Just a second. Okay. Uh, so other challenge which we face during the filter design is to maintain the quality of power being injected into RTDS. Otherwise, it may lead to instability of the converter also. Another thing here is that appropriate interconnecting impedance value. Because if we don't connect in a proper way, then it may happen that it can lead to a connection of a physical inverter to a weak grid, and it will lead to various challenges, various things in the grid. Then comes the errors in the PHIL. Now what happens here is that whenever we simulate the system on a PHIL, there are various possible causes of errors can happen, like transformation for the connection of both system. Okay, accuracy of the sensors and their related scaling factor, because in previous we have shown here that there we have to scale the factor. So whenever we are going to scale, the scaling of the factors of various things must be done properly. Now, another here is the scaling factor associated with GTAO and a GTAI of a RTDS. So these are all, the challenges faced in FPGA level for control formulation, filter designing of interface, appropriate interconnecting impedance value, probable cause of error during PHIL. Now coming to the applicability of a described model for other testing scenario. So now what happens here is that how we can implement this described model for various scenarios, like I would here. So basically, how we can extend this described model and connect and simulate on different testing scenarios, or we can say cases. So basically, what we can do here, because in this work we have not considered the uncertainty. Okay, so basically also we can also integrate the uncertainties associated with PV. Okay, Th- th- this is not being done in this described model. Okay, इससे क्या होगा, जो हमारा मॉडल बनेगा, इट विल बी more practical and can also be used for the practical implementation. Okay, so basically I will share some points over here. तो इस तरीके से हम ये जो मॉडल हमने डिस्क्राइब करा है, इसको हम एक्सटेंड कर सकते हैं फॉर द वेरियस टेस्टिंग सिनारियो, लाइक हम अनसर्टेनिटीज लगा सकते हैं. व्हाई वी आर टॉकिंग अबाउट अनसर्टेनिटी? Because in a renewable energy generation, basically in this we have taken solar PV, solar photovoltaic. So basically what happened here is that the energy which is generated is dependent on different parameters, like is dependent on different parameters like voltage, okay, voltage, current. It also dependent upon the irradiance of the साइट जहाँ पे लगाया जा रहा है सोलर, क्योंकि अगर हम अलग अलग जगह के सोलर्स लगाएंगे फॉर अ लार्जर ज्योग्राफिकल एरिया, तो इनकी सोलर इरेडियंस डिफरेंट हो जाएगी. तो इसीलिए एक बड़े से एरिया को कवर करने के लिए हमको जो अनसर्टेनिटीज हैं रिगार्डिंग दीज, वी शुड बी testing that. We should also include that, because otherwise, if we don't include that, then the practicality of our model will get reduced. So these are all. Also, there is another thing which is temperature. What happened here is that whenever the solar panels, they work in a uh, they work in a described temperature range. So if the temperature gets so much high, so it's so much high that it is greater than the operating, or we say allowable limit of the temperature, then what will happen here is that the PV generation output will reduce. Okay, PV generation output will get reduced. So in order to to have a optimized PV generation, we should be carefully checking whether it should not be operating above the allowable limits. Also, irradiance, or I would say the weather condition play a very important role on the PV generation. Like if there is cloudy, then the PV generation will be low, will be low. Okay, so if it is sunny and the temperature is good, means ambient temperature, PV generation will be optimized, or I would say maximized, will be maximum. Okay, these are all the regarding the uncertainties of the PV. Now another thing here is that we can also integrate various optimization algorithm, various optimization algorithm, like for various volt war control, or for the power loss minimization, power loss minimization. We can also integrate these things in our described models, like how we can reduce the power. Also, we can also includes electric vehicles in the distribution network. Like nowadays, there are various, electric vehicles are increasing. So what happened here is that electric vehicles are, you know, a dynamic load. It's a dynamic load. It comes at a certain time, but with higher magnitude. Okay. So basically, it will we can also make our system more practical by integrating EVs in the distribution network. Also, we can integrate the cyber security aspect of the network, like how the security of the system is can be increased. For this, what we have to do, we have to estimate the states, because the state estimation helps in estimating the states of the power system or any distribution system. Then from the here, what are the state? Voltage and angle. Basically, from there we can compare it from the reference values or the nominal values, and we can we can conclude whether the system is stable or not. Okay, so basically what happened is there during the cyber, any attack or like that, these values get destroyed. Okay, and if we match it from the reference value, they will not be closer. So basically what we take here, we measured minus v reference. If those values are not in the allowable limit, then we can say, okay, our system is compromised, we have to do something like that. Okay, so basically it will also help in we can also integrate the cyber security aspect. Okay, so also we can, for testing and for testing purpose, we can also increase, sorry, let me write it again. We can also increase the concentration of we say PV and BSS integration. Okay, for increased penetration. Like in this, we have used only 5 sites of BES. Okay, and what we have used in this model, we have used just a second. Okay, we have used 5 sites for BESS and 35 different locations for uh, solar PV. So for a more realistic, for a more realistic network, we can increase the number of solar PV locations. Okay, and BSS also. So what it will do, it will lead to a more practical uh, network. So this shows that the described model can be extended or it can be used to apply it. It will serve as a basis for other various scenarios. Like there is another aspect to that. We can, we can test the controller, testing of the controller's prototype in recreated operating conditions. Okay, like using low voltage network simulator or advanced metering infrastructure, or we can use the communication infrastructure in the network also. Okay, this is how we can, you know move we can, apply the described model. Now coming towards the applicability of a testing, like testing controller in a recreated operating condition where AMI or all these things can be used. So basically this shows the network schematic of a of that applicability. This is the RTDS, which is a model of a distribution network which is connected through GTA cards. GTA 1 card, 2, there is these are input cards. It is connected through this, and there is AMI, advanced metering infrastructure, is being done here, and which is connected through a GSM communication interface. So basically, there are various types of these are the fiber optics. These all are blue lines are the fiber optics, and the red ones are the 400 watt AC, and these are the GSM communication lines. Okay, so what we conclude from here is that the offline simulation can be impractical due to amount of computational resources needed to solve network. While using RMS test cases, transients present in a modern power system may be neglected. Modern energy conversion systems require an enhanced level of detail in order to properly present their behavior. Moreover, due to steady increase of non-synchronous generation, new operation and the management strategies need to be tested to ensure power system security. These constraints can be overcome by using real-time digital simulations which allow to obtain the high precision in a time frame. So basically, we can here see that this is RMS domain, observed dynamics, commercials, EMT. Then comes the EMT based real-time simulations. Okay, so basically what happens here and there when we use RMS, the domain is like phasor, but in EMT, the domain is time. But in the real time simulation EMT, the domain is also time. But in RMS, we observe electrochemical and mechanical and quasi steady state. But in EMT and RTS EMT, we observe the electromagnetic and the electromechanical dynamics. Basically, the execution times in RMS lead to second to hours. Okay, but in EMS, it also seem like that. But in real time simulation, it is a real time. Where these are used. RMS is used generally for system planning and stability issues, steady state analysis. But EMT is generally used for the slow and fast transient analysis. Okay, but RTS and EMT generally use where the integration of the power electronic devices. Okay, now what are the lessons we learned from here? So basically, utility impedance changes such as cables, transformers, and load behavior causes influences on the controller tuning. Basically, what happens here? Some due to change in the impedances of cables and transformer, or basically the behavior of the load, the controller tuning has to be changed for everything, for every load impedance. Okay, so it was detected in condition like with and without transformer connection, interconnection between the system that shows the distinct response of output voltage power. Therefore, regarding the controllability of the system should be developed and the further studies should be done for this topic. Okay, it has been observed that the lower the simulated impedance and the higher the hardware impedance, the better the stability of the system is there. Therefore, the addition of hardware inductance and reduction of additional interface filters implemented in the hardware proved to be useful. Okay, another thing which I would like to hear discuss is that we have already talked about SHIL and PHIL. Okay, actually PHIL, it is a power hardware which is in a high power devices are used. Okay, so actually it gives higher fidelity than simulation only studies. So than simulation only studies. And the advantage for the PHIL is that we can model various real power networks to study any particular case or scenario. Okay, this is the thing. Another here is that due to the hardware constraint, because implementation of a hardware is a very difficult thing due to hardware constraints for real time computation, for real time computation. So basically, and real time computation of large and complex power system, actually what they require, they require the electrical model is split into different hardware devices. Okay, like, okay, hardware into different hardware devices. Okay, and basically, like across CPU cores. Okay, कि ये कोर इस चीज को मॉडल करेगी, डिफरेंट कोर विल मॉडल द डिफरेंट इलेक्ट्रिकल मॉडल्स. ओके, और जब हम इन मॉडल्स को स्प्लिट करते हैं, देन देयर इज अ डिले विच इज नोन एज बर्गेरियन स्टब लाइन. बर्गेरियन स्टब लाइन. Okay, it introduces a section of impedance so that the time of the signal to travel along exceed one time to allow the communication signal between the devices. इससे क्या होता है कि जो पावर का सिग्नल है, मतलब जो कोई भी सिग्नल है, वो अगर मूव करेगा तो इससे जो डिले होगा वो अलाउ करेगा. व्हाट इट विल डू, इट विल अलाउ टाइम फॉर द कम्युनिकेशन ऑफ द सिग्नल. ओके, उन दोनों डिवाइसेस के बीच में. ठीक है, तो therefore time delay should be considered when we planning for a control strategy like this. Okay, so I think in the this last lecture of this there is nothing more than that. Basically it's all about the hardware implementation like that. Okay, and I believe we should have gone through the videos already, basically to get a detailed you know idea about how this is all works. Here I have, just recap a smaller part of it. Then we will solve some questions also. I think this is the last topic of your lecture. Okay, this is the 12th lecture because it's a 12-week course. So basically, now I will, introduce something. Okay, which is a energy management, like how do we peak energy management strategy. We have discussed about it in previous section, but still it is in the lecture, so I will go through it in a bit. Then after that we will solve some question. Actually what happens here is that, because I have already told you about the renewable energy generation, I have already talked you about the renewable energy generation. Okay, so let's say there is a curve, एक कर्व है. This curve is of power versus, I would say, time. Okay, this is of a time. Okay, now what happens here is this, it will show that with the time there is a certain energy demand. Okay, there are various peaks, sub peaks, there is a valley region, or there is another curve like this. This is a, you know, load demand, or I would say load curve. लोड कर्व, ओके। तो ये एक तरीके का लोड कर्व है जो भी किसी भी माइक्रो डिस्ट्रीब्यूशन नेटवर्क का हो सकता है। तो इफ वी आर गोइंग टू इंटीग्रेट renewable energy sources, then we should also know about how that renewable energy is going to generate this energy. So let's say that energy has a curve like this. For example, solar. This is 12 a.m. This is, you know, midnight, I would say. This is afternoon, and this is again midnight. Okay, a full 24 hours. I would say 0 to 24, and this is 12. Okay, basically. So I will show you how the energy management works. This is 12. Okay. So basically, with the time, initially the solar energy is very minuscule, or I would say very low. Then after that it goes on increasing like this, and this is something like this goes like, okay. This is a typical solar energy curve. As you can see here, initially the generation by the solar energy is very low. Then after some time, it gets on increasing. Okay, it goes on increasing like this. Okay, so you can clearly see from here to here. This is the surplus energy. Why it is surplus? Because the load demand is much lesser than the energy generated by the solar. So this energy is can be stored in the battery and will be used at that time when the energy demand is higher, like here. Okay, okay, like here. It can also be used here after the storage. So basically, I will draw one line over here also. This is a you know energy generation curve they show. So basically, it shows that if we use this energy here, then what will happen here is that our demand satisfaction from the conventional energy will get reduced. So if we use solar PV energy from battery storage, what it will do, it will lead to lower congestion of power network. Okay, so basically what happens here is that it will help also help in reduction of fossil fuel based generation. ओके, इससे क्या होगा, अब जब यहाँ पे हमें जो भी अमाउंट ऑफ एनर्जी फॉसिल फ्यूल से चाहिए होगी, इफ इट दैट टाइप ऑफ एनर्जी इज सप्लाइड by the solar energy, then the dependency of the on the fossil fuel, because ये क्या है, ये fossil fuel based generation ही तो है, ओके okay? इस पे डिपेंडेंसी हमारी कम हो जाएगी. सो आई वुड से इट विल लाइक दिस. सो this much amount of del P will not be coming from the fossil fuel. So it will help in the decarbonization. Now, it also helps in the, it also helps in, now, why are we storing energy in battery? इसका रीजन क्या है? फर्स्ट ऑफ द रीजन है ये, इट स्टोर्स सरप्लस एनर्जी. ओके, पहली बात तो ये. सेकेंड थिंग इज दैट इट ऑल्सो हेल्प इन वोल्टेज कंट्रोल. क्यों? क्योंकि अगर हमारे नेटवर्क में हायर अमाउंट ऑफ एनर्जी अवेलेबल होगी, it exceeds the load demand, the system voltage will rise and it will lead to a various outages. So, in order to take control of the voltage control techniques must be used, and therefore the extra energy is stored in the battery. Okay. Another thing is that it helps in managing the intermittency or stochastic nature of PV. Reason? See, you can see from here, I will remove some of the things. Okay. You can see here, see, the load demand is at this point. There is a load demand here, there is a peak here, let's say P1, this is P2. अब इस टाइम पे हमारे पास एनर्जी डिमांड इज हायर, विच इज मच हायर देन द एट 12 PM. ओके, तो क्या होता है कि इस टाइम पे सोलर नहीं है, so we cannot satisfy this demand from the solar or any wind. So only options we left here is that we have to supply it from the fossil fuel. अब ऐसा क्यों है? क्योंकि इंटरमिटेंसी है, क्योंकि जो सोलर है इट इज बेस्ड अपॉन द, इट इज बेस्ड ऑन solar radiation, and solar radiation will come up from here 10 to 4 to 5 in summer. So इसीलिए अगर हम बैटरी मैनेजमेंट सिस्टम इस्तेमाल करेंगे, बैटरी स्टोरेज सिस्टम इस्तेमाल करेंगे, वी कैन सप्लाई दीज पीक्स from the solar power stored in the energy. So that's why it helps in managing the intermittency or stochastic nature of the PV. अब इससे क्या होता है, जब हम PV का इसको करेंगे, इससे क्या होगा, हमारा पीक शेविंग ऑफ लोड हैपेंस. इससे क्या होगा कि जो हमारी पीक्स बन रही थी, लेट्स से ये पीक जो बन रही थी, ये अब पीक नहीं रहेंगी. क्यों? क्योंकि दीज आर सप्लाइड बाय द सोलर एनर्जी. सो इफ वी क्लियरली सी हियर, it will be like this. It will be like this. So basically, if we draw a peak on the perspective of the fossil fuel, so there will be no peak. Why? Because this region is supplied by the solar energy. This is also one of the benefit of the battery. Another thing is that it helps in reduction of line losses. Actually, P is directly proportional to, obviously P is equal to I square R, or I would say P is directly proportional to R. So R is rho L by A. It is directly proportional to length of the conductor. So if the length of the conductor increases, power losses will increase. So basically, if we, let's say, this is the point A, this is point B, this is point C, and the fossil fuel is coming, is supplying, you know, energy from here to A, to B, and to C. Let's say this is X, this is 2X, this is 3X, the length. So if the current is flowing from here, it will reach A point, B point, and C point. So the power losses in all these PA, PB, PC will be much higher if the load is satisfied at these load center from the solar which is installed nearby to these load center. So if the losses by the solar PV is P dash A plus P dash B plus P dash C, it will be much less than the losses happen due to the fossil fuels. So basically, it will lead to a reduction in the line losses. Okay, so there is a, I will show you a PPT where, just a second. Okay, so what happens here in this? In this, a real-time analysis, just a second, a real-time analysis of distribution network with solar PV is done. It is done on same IIT Roorkee network when where these are the all these solar are there. There are also batteries connected. Same system which I have just described before. It shows the real-time voltage variation with the PV integration. Okay, so basically overvoltage signifies high PV penetration with a highly loaded condition. So basically, in first, this shows for the spring season. This is for the spring season. This is for summer, and this is for autumn. Okay, so it shows the variation of the voltage for you know all these nodes. These are all in the x-axis. They are nodes. So each node there is a maximum value. Over voltage is happening, and there is some under voltages also. More accurately, this shows the real-time voltage variation with a PV integration. So a linearized AC model is used to observe the effect of 200 kilowatt battery ampere kilowatt hour battery installation at the node 92 at the substation. Voltage variation for all the nodes of the three representative days are shown in the figure. अब क्या है कि तीन वोल्टेज वेरिएशन शोन फॉर द टू एक्सट्रीम आवर्स कौन से एक 30th 1 बजे and 22. So you can see here the variation. This is red one shows the variation of the voltage at 22 hour. Okay, this is lesser than in comparison to the voltage variation at the 30th hour. Why? Because at 30th hour the PV integration is there, so a slightly higher voltage will be there. Okay. Now require a reverse flow is shown through this. और ये क्या है बैटरी पावर एंड एनर्जी ट्रेडिंग है एनर्जी रेटिंग्स इतनी है अलग अलग लोकेशंस पे इसकी ओके दिस शोज another one shows here is the 30th hour and 23rd hour. You can clearly see in the 30th hour means in day the voltage is slightly higher in comparison to the voltage at the 23rd hour which is in in night. Okay, so this is the PHIL implementation of that, where battery emulator is there. Same, okay. The physical BSS is integrated. This is a microgrid architecture. These are the diesel generator. This is rooftop. This is battery. This is grid, and this is electrical engineering department. In this, the load of the department is 1 kilowatt. Rooftop solar maximum generation is 170. Lithium ion battery rating is 20 and 200 kilowatt hour. Okay, so this is a brief description of that. After that, I would like to solve some questions regarding this. Okay, then we will end our lecture. So the questions, I will write it some questions here, and you have to answer that. Okay, you can write this them in the chat box also. Okay, so question number one: what is the key challenge, advantage of using DC microgrid over an AC microgrid? Okay, first, reduce losses. B, easier integration with traditional grid. C, requires more complex control system. D, more expensive or less economical. So write in the answer, which is the key advantage of using DC microwave. A. यस, क्योंकि क्या है, डीसी माइक्रोग्रिड में लॉसेस कम होते हैं, इट इज करेक्ट, लेकिन easier integration with a traditional grid is not easier because it is a DC and traditional grid is AC, so we have to use various type of inverters, converters like that. Require more complex control system, no, it is also not an advantage. More expensive and less economical, yes. It's not like that because complex control systems are used for a AC microwave. So from the perspective of the question, the correct answer is A. What is the benefit of virtual power plant in a smart grid? Okay. A, Wind turbine. B. Solar panels. C. Hydropower. D. Traditional coal power plant. So, give me that answer. So, what is the benefit of the virtual power plant in a smart grid? Sorry. Actually, I wrote a wrong question. Sorry. Extremely sorry for that. Which of the following is not a part of DER, distributed energy resources? So the question is different. I wrote the different options. Sorry about that. You have to write which of the give the answer to that. Which of the following is not a part of DER? So basically, core power plants are not the part of a distributed energy power plant. Okay. So question number three. Which of the following is a benefit of virtual power plant in smart grid? First, require fewer resource. B, aggregates multiple energy sources to act as one. Okay. C, reduces the need for renewable energy sources. D, none. Yes. Aggregate different energy sources to act as a one. Question number four. In a smart grid, just a battery energy system has different advantages. Which of the following option correctly describe? A. Voltage control. B. Reduces intermittency of renewable energy source. C. Loss reduction. D. All of it. Yes. So D is the correct option. Okay. Which of the following technologies supports ancillary service in smart grid? Hydraulic pump, virtual synchronous generators, C. LED lighting system, D. No. So give me the correct answer. Okay, so this is I have told you about in the lecture. The virtual synchronous generator is support used as an ancillary services in the smart grid. This is the clear direct answer. So now six is the prosumers. Prosumers in a smart grid refers to a consumers who passively use electricity. B. Power plant operators. C. Consumers who produce and consume electricity. D. None. Okay. Yes. The correct option is C. Prosumers उसे कहते हैं जो produce भी करते हैं consumes भी. So this is the correct answer. What is economic dispatch? Okay. First, reduction of power dispatch. B. Optimized power dispatched for meeting generating demand. Okay. C. Both. D. None. Yes, this is the correct answer. Question number 8. Which factor is most important for optimizing the economic dispatch of power? Smart grid. पहला, number of consumers. B. Age of power plant. C. Electricity prices. D. Renewable energy sources capacity.
तो बेसिकली इसमें क्या है, सबसे इम्पोर्टेंट क्या होता है, इलेक्ट्रिसिटी प्राइसेस होते हैं, विच इज वेरी मच इम्पोर्टेंट. सो क्वेश्चन नंबर 9. What is the most important element of PHIL setup? ओके, पहला है पावर एम्पलीफायर, बी GTAO कार्ड, सी वोल्टेज एंड करंट सेंसर, डी ऑल ऑफ द above. Okay, yes, all of the above. इम्पोर्टेंट एलिमेंट क्या होता है, पावर एम्पलीफायर भी होता है, GTO कार्ड, आउटपुट कार्ड होता है, वोल्ट सेंस, सब जो है इज वेरी मच इम्पोर्टेंट इन द PHIL सेटअप. क्वेश्चन नंबर 10, मैच द फॉलोइंग. Okay, what do I have to match? First, DFIG, second, RTDS, third, PHIL, fourth, FPGA, fifth, HIL. One, it is field programmable gate arrays. Two, hardware new. Third, real-time device simulator. Four, doubly fed induction generators. Fifth is real-time digital simulator. So basically, A is 1 5, second 3, third 4, fourth 1, and fifth 2. B 1 5, second 6, third 4th, fourth 1, fifth 2. Then I would write C, which is 1 5, second 6, okay, third 6th, sorry, just a second. Third 4th, fourth 2, and fifth 1. So D, none of the above. So give me the correct answer. I think one I have left today. One, two, three, four, five. Just a second. Okay, okay, just a second. I have to rename these numbers. One, two, three. Four is power and higher. Actually, four is P power hardware in loop. Actually, this is fourth, then fifth and sixth, then fifth and sixth. Okay. Okay. Now, okay. Okay. Now I will solve it for you. So basically, क्या है कि DFIG किसको कहते हैं? इट इज डबली फेड इंडक्शन generator. Okay. Then comes RTDS. It is real time digital simulator. Then PHIL. Okay. Which is power hardware in loop. Okay. Then comes the FPGA. It is field programmable gate arrays. FPGA. Then comes HIL. It is hardware in loop. तो अगर हम आंसर देखें तो क्या होगा? फर्स्ट का 5 होगा, ठीक है, सेकंड का 6 होगा, थर्ड का 4th होगा, और फोर्थ का फर्स्ट होगा, एंड फिफ्थ का 2 होगा, ठीक है। तो ये हमारा करेक्ट ऑप्शन है। नाउ अनदर क्वेश्चन इज क्वेश्चन नंबर 12. आइडेंटिफाई करेक्ट स्टेटमेंट्स। ओके, पहला स्टेटमेंट है ए, मैक्सिमम solar power injection during off-peak load hours may result in under voltage. Okay. Peak load hours with little or no solar power may result in under voltage. C. Reverse power flow is not possible in active distribution networks. D. None of the statements are correct. So give me that answer. Okay. So basically क्या होता है कि मैक्सिमम सोलर पावर इंजेक्शन ड्यूरिंग ऑफ पीक आवर्स में रिजल्ट इन अंडर वोल्टेज। नो, जब मैक्सिमम पावर इंजेक्शन होगा तो वो होगा, अगर ऑफ पीक आवर में हो रहा है तो अंडर वोल्टेज नहीं रहेगा, इट इज ऑलवेज ओवर वोल्टेज। क्यों? क्योंकि वोल्ट देयर इज अ एक्सेस डिमांड अवेलेबल इन अ distribution network. Peak load hours with little or no solar power may result in under, yes, it, अगर सोलर पावर कम है
So excess power demand is not in the distribution system, and it may lead towards the undervoltage. Yes, it is correct. Reverse power flow is not possible. No, no, it is a wrong. Reverse power flow is possible in the distribution network. Okay. So now the question number 30. BSS has proven to be an effective solution for voltage control. Okay. B. Flattening of load curve. C. Reduction in power loss. D. All of the above. Give me the correct answer. Yes. BSS से क्या होता है? वोल्टेज कंट्रोल करते हैं कि एक्सेस पावर डिमांड होती है तो हम उसको वोल्टेज कंट्रोल करते, फ्लैटनिंग ऑफ लोड कर्व। हाँ, क्योंकि जब पीक डिमांड हो रही होती है उस टाइम बीएसएस एनर्जी प्रोवाइड करा के लोड कर्व को फ्लैट कर देते, पावर लॉस का रिडक्शन कर देता है, क्योंकि बिकॉज इट सप्लाई एनर्जी फ्रॉम अ लोकलाइज्ड पॉइंट्स विच इज नियरर टू द लोड सेंटर. So basically D, all of the above is the right answer. What the smart grid R&D areas under cyber security? पहला है seamless grid operation involving transmission and distribution system operators, reliable wired and wireless communication technologies, coordination and control of multiple converters. D, all of the above. Give me the correct answer. देखो साइबर सिक्योरिटी के एरियाज जो हैं उसमें ऑल ऑफ द अबव, नो 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 नॉट, नहीं देखो साइबर सिक्योरिटी के एरियाज में क्या है कि ये जो पहला है सीमलेस ग्रिड इंटीग्रेशन, इट इज रिगार्डिंग द not the cyber security but the power system stability. Okay. Reliable wired and wireless communication, it comes under the area of a cyber security. So B is the correct answer. Okay. What are the primary goals of Indian smart grid pilot projects in the distribution system? Okay. First one, incorporating AMI. B, incorporating OMS. What is outage management system? Incorporating peak load management, or D, all of the above. Okay.
Yes, ठीक है, ये सब एडवांस EMI क्या है, एडवांस्ड मीटरिंग इंफ्रास्ट्रक्चर, OMS outage, ये सब जो है, these are the pilot products projects for the Indian smart grid. So question number 16, what are the probable cause of error in the PHIL setup? ठीक है, A, accuracy of measuring sensors and their related scaling factors. B, scaling factors associated with GTAO and GTAI of RTDs, input and output cards. C, both. D, none. Yes. So basically, measuring sensors की accuracy जो है is very much probable cause for the errors. Scaling factors जो associate करे जाते हैं output input से RTDS के, they are also very much, you know, causes of error in any PHIL setup. So next question is, the excess demand, load demand in active distribution networks results in, पहला, voltage rise and
reverse power flow. B. Voltage sag and reverse power flow. C. Voltage rise only. D. Voltage sag. तो बेसिकली क्या होता है जब एक्सेस डिमांड होती है तो मीन्स कि लोड डिमांड जो है लोड ज़्यादा है जनरेशन तो बेसिकली व्हाट हैपन हियर इज दैट वोल्टेज सैग विल हैपन ओके और अगर जस्ट लोड डिमांड ज़्यादा है जनरेशन से तो क्या होगा सैग हैपन व्हाट विल हैपन सैग और इफ लोड डिमांड is less than generations, then voltage rise will happen. Okay, voltage rise will happen. So another question, question number 18. What are the objectives of a smart city? First, demonstrative future capabilities. B. Renewable energy integration with off and on grid technology, advanced metering infrastructure. D. All of the above. So give me the correct answer. Yes. तो क्या होता है कि स्मार्ट सिटी में क्या होना चाहिए फ्यूचर कैपेबिलिटीज भी होनी चाहिए लाइक फ्यूचर में कोई चेंजेस होने वाले हो दैट शुड आल्सो बी इंटीग्रेटेड कैन बी इंटीग्रेटेड इन दैट सिटी लाइक ईवीज इंटीग्रेशन और समथिंग लाइक दैट renewable energy integration होना चाहिए because it will lead to a decarbonization of economy and advanced metering infrastructure means metering infrastructure होना चाहिए so all these must be there for any smart city. Next question, question number 19. Power flow, control of DC microgrid falls in which type or exactly which layer of control? First, tertiary. B. Secondary. C. Primary. And D. Zero level. So basically, this type of flow control generally falls in the layer of the tertiary control. Okay. So another question here is, which is question number 20. What is the role of demand response in smart grid? First, to increase energy production. B, to balance energy consumption with generation. C, to decrease electricity price. D, none. So give me this last question answer. बी, यस। क्या होता है, डिमांड रिस्पॉन्स क्या करता है कि बैलेंस करता है कंजप्शन को विद रिस्पेक्ट टू जनरेशन। ठीक है ना, तो इसीलिए इसको हम कहेंगे डिमांड रिस्पॉन्स टू बैलेंस एनर्जी कंजप्शन विद द जनरेशन। So far what we have learned here in this, we have gone through the smart grid. Okay, why there in the smart grid there is advanced metering infrastructure, renewable energy sources, EVs. Then we also talked about the microgrid. There are different types of microgrid, AC and DC. What are their benefits? Which is much more economical, which is not. Okay, so we have talked about all these things in the lecture. So thank you very much. I hope you have liked this session. If you have any question, you can ask me. Thank you. Okay, you can leave if you want. Thank you very much.